I'm here to present a Kaggle competition that we did in kind of our 10% time at Deutsche Bank, me and a couple of guys at work to improve our data science. And I thought it'd be a nice kind of story to go through to show off like how to do an analytics project from start to finish and how to improve your data science using Kaggle, because I think it's a great learning tool. So first of all, what is Kaggle? So I'm not just saying random words at you. So it's a website that hosts machine learning competitions. So basically, companies come along with a data set, usually a large data set, and a very, very specific question that they want to answer. And it's a specific measurable question. So how relevant is a search term to a product, for example? And then everyone can download the data set, make a predictive model, make a prediction on a test set, and then everyone gets ranked on how well they've done on their prediction versus the true answer. And the top few people usually win a bit of money, but the top few people are usually some of the best data scientists in the world. But it's great because you can learn from them. Okay. So I thought it'd be interesting to talk about that here, because like I said, it's a nice kind of story of data science from end to end. So they've taken out a lot of the difficult part of the exploring the data and finding what questions to ask about the data. They've given you the answer. So a lot of data science work is finding what question to ask. So here you get the fun part. You get to play with the model, and you get to see what sort of predictive models you can use. So today, hopefully, we'll learn the basics of predictive modeling if you're not familiar with it, how to design a basic predictive model pipeline, and like the basics of text analytics, and hopefully. So what is the question that was in this competition? So it was search relevance for Home Depot. So Home Depot wanted to improve their search engine. So basically, when a 10-year-old kid sitting on phone books is searching for fiberglass insulation on the Home Depot website, there's a list of possible results that can be returned. So the search engine will return some number of results. And so if Home Depot want to improve their search engine, they have to decide how good or bad the results that they're returning are. And that takes human input. So 3 people will review the search term and the potential returned product, and say how relevant that product is to the person's search term. So fiberglass insulation is pretty relevant to all of these things. So it's a rating between 1, not really relevant, 2, kind of relevant, 3, very relevant. And then it's average, so you get numbers like 2.66, etc. So the problem for Home Depot is that that's time-consuming and expensive. So what they want to do is remove the human input and start building a predictive model around predicting relevance and using that to help their search engine. And so you and I know that means data science. So what was the data that you were using to predict this relevance? So you're giving a training set of information, and so you've got for each product. For here, for example, this insulation again. For each product, you have some information about the product title, usually product descriptions, and loads of information from the Home Depot website. And the search terms that people have typed in to get back those products. And so you can see there's some badly spelled ones and just generic kind of search terms. And then humans have rated how relevant those search terms are to the product title. So you have a training set that gives you the answer, tells you what the relevance is, and you use that to train your model. And then you have a test set where you're trying to predict the relevance. And Home Depot know the answer, or Kaggle knows the answer, and you're trying to predict against that. So how do you start? It's daunting. There's a lot of information. There's a lot of words and product IDs, and it's kind of difficult to know where to start at the beginning. So a good start is just randomly guess. So just chuck in random numbers for relevance between 1 and 3 and see what happens. And so we got an error of 1.481, 2,000 place. Terrible result. But it's important because now you've got a benchmark to know what the randomly guessing will get you. And you know if your model is getting a worse error than that, then you're doing a terrible job, so you have to go back to the drawing board. So it's good to set up that benchmark, and usually there's some benchmarks on there to let you know, like, if you're doing worse than this, you're doing a bad job. So let's do better. Let's see how we can actually predict some relevance. So a simple one is like, right, if there's words that are in the search term that are also in the product title, that's probably a relevant search term. So if I've searched for insulation and insulation is in the product, that's probably a relevant search term, right? So we can count the number of words that overlap between the search term and the product title. And you can see that there isn't really much of a correlation between the relevance and the number of words that overlap. So this guy only has 1 overlapping, but it's very relevant. This has 3 overlapping, and it's not quite as relevant. So it's not very well correlated. So maybe we need to do like a ratio. Maybe it's not the number of words; it's the fraction of words that are similar between the two of them. And again, that's not really a great kind of predictor. So maybe this is a bad example I've picked. So let's take a look at the entire data set and look at the ratio of overlapping search term words for the whole set. And you can see again that it's not really great. It's kind of random. It's all over the shop. So the number of, the fraction of words that overlap doesn't really look like it correlates that well. But actually, if we fit a line to it, then we can kind of see there's a bit of predictive power there, ever so slightly. So there's an increase, a slight increase. As ratio increases, the relevance slightly increases. So let's just take that. Let's see how this really, really basic, bare bones, simple model works. So here we're going to predict relevance is equal to 0.68 times the ratio plus 1.914. And so that's enough to get you an error of pretty much 0.05. So that tells you if your relevance is somewhere between 1 and 3, and if your relevance is your predicted relevance is relevance plus or minus 0.49. So it's not great. You're not really doing that great of a job of relevance, but it's a very simple model. And but we're going up 500 places, so we're not doing too bad. But funny enough, actually, if you look at the best model in the whole competition, the final result, they've got an error of 0.43. So even with, you'll see the model at the end, it's a really, really complicated model, huge amount of effort, huge amount of processing, and there's not that much of a decrease in error. So there's obviously a tipping point there for if you're doing this in production of, right, we can use a really, really simple model or we can use a really, really hardcore model, but somewhere in the middle there is a model that's good enough, and it's deciding on where that good enough spot is, where the amount of effort you're willing to put in versus the decrease in error you're going to get. So for me, I'm lazy, so I might have stuck with the simple model to begin. I don't know. So how do we get better? How do we move on and start really, really getting into the machine learning part of this? So first part is clean the data. As you've seen there was a lot of spelling mistakes. Those 10-year-olds, they've got small fingers. They can't type in insulation really well. So you got to clean the data and get the data into a more standardized format. So add more features. So we just had that ratio of the overlapping words. How can we add more features? How can we decide how can we, in a numeric form, say whether the search term and the product are relevant or not? Start to use more flexible models. You could see my linear line is a terrible model for that really random looking plot. So how do we use better machine learning models to eke out better performance? And what I'm not going to talk about today, but what's really important for these competitions is using a good validation set. So you want to take that training set and split it in some way so that you train a model on, let's say, 70% of the training and look at the result on the other 30%. And then you get an idea of how good you're doing, what sort of hyperparameters you should use. And each competition that you do is going to be different because they're going to slice and dice the data that they give you in a different way. So it really kind of separates the top people from the middle people, a really, really good validation set and how to split it. And you could do a whole talk on that, so I won't do it here. But yeah, it's really interesting. So how do we clean the data? So simple things that you can do in Python: remove punctuation, put everything to lowercase so that when you're comparing, comparison is easier. So standardized measurements like inch and in goes to in or some standard format, because we're talking about Home Depot, we're talking about products. You want to standardize everything that people are looking for. Removal of stop words, that's a simple one if you're not familiar with that. It's removing words like and, the, or. They're not. If and is in the search term and is in the product name, that's not really going to tell you much that they're similar or not. So if you get rid of them, it increases your actually there. And then stemming words. So taking words like metal, metallic, and metals, and changing them all to metal, so that when you're doing your comparison of are words the same, that you're not saying no, metallic is not the same as metal, when pretty much it is, you know, for predicting relevance. Yeah.
I think it's important to change in to in dot, because in can also be like a connection words.
So I think that's why we put in the, if I remember, that's why I put in the in dot, so that the in wasn't getting chucked out. So in dot will stay in there, because you're kind of like, you're indicating that that's not in, that's inch. And we try, it was a regex, so you were trying to do like 2 space in, that will go to 2 space in dot. So you're trying to say like, oh, this is a measurement, not the word in. So you can use, so there's loads of, NLTK is a text, natural language processing package in Python, and I think there's a workshop on that later, so I think they'll go into way more detail about it, but there's that NLTK is really useful for this standardization process and getting words that in all of the data down to a standard form. So getting spelling errors. So there's an open source package you can get from GitHub called Hunspell, but a guy did a really nice little function on the Kaggle website where he literally just took every search term that anyone had done, queried it in Google and used the like, did you mean like X, and returned that and made a dictionary out of that. And that was his spell check, and it actually worked way better than that, because Google has, you know, puts a lot of effort into getting spell checks. So like the really simple things like that, you like this, that, I'll come back to it at the end. But the things you pick up from people on the Kaggle website are just really great. So that's a really nice thing about it. So once you've got the data, and you're happy with your pre-processing, you've got the search terms and the product description, the product titles into a standard form that you can kind of easily compare and say, right, they're similar or not. Then you have to do some feature engineering. So whereas before our feature before was the ratio of overlapping words, we want to go deeper into that and get a better idea of how to do the similarity. So feature engineering is really important for this, and probably for this one it was way more important than the models. And for most of the ones I've come across, the feature engineering is the real deciding part of how you change the input data they give you and put it in a format that the computer can say this is relevant or not. So looking at where we did the overlap of words before, right? So we did that kind of like we did it using a Python for words in search term or words in product title, for example. But you want to do that in a more efficient way. So what you can build is something called a term frequency matrix. So you build a matrix which is all of your products, let's say. So this is a product ID, and then the columns of your matrix are all of the words in your vocabulary. And for the product, you count the ijth part of the matrix is how many times that word turns up in the product description. So you can see Owens Corning R19 craft faced insulation bats is in here. Owens Corning is in this product, and it's something else, insulation blow-in or something like that. So you build this giant matrix of the occurrences of words, right? And then just doing you can do the same thing for the search terms, and then doing a simple dot product between the two matrices gets you the exact same result as you did for words in search term. Are they in the product title? So it's just a simple dot product, and it does it really efficiently. Standard libraries help build these very quickly. So sklearn has a little module. It has loads of amazing modules that really help out. So you can see in 2 lines, I can build this document term matrix with a lot of different options in it. And the nice thing about this, as well as being efficiency, it kind of sets the stage for the fancier methods we're going to look at down the line, because you've got this like giant numeric matrix, and we're going to get some features out of it. Engrams is a really important part. So here I split the product title into words. Okay, so another way to do it is instead of splitting by space, that's how you split by word, space, or punctuation, you can do what's called engrams. So that's just the characters. So we use characters of length 3 or 4. So for an engram is an engram of length 3 is 3 characters in a row. So for example here, Deutsche Bank would be split into the engrams DEU, EUT, UTS all the way across. And the advantage of using Engrams is it helps protect against spelling errors. So if we were to compare Deutsche Bank and Cheese Bank together using, or Deutsche Bank and Deutsche Bank here, if you're just using words, they would all be, the bottom two would be 50% similar to the top guy, right? And it's only a very simple spelling mistake down the bottom. Whereas if you use the Engrams, you can see there's a much higher overlap between Deutsche Bank and Deutsche Bank and compared to Cheese Bank and Deutsche Bank. So it's a really quick and dirty way. If you don't want to do the spelling checking, or the spelling checking isn't working that well, you can use these Engrams, and it really robustifies you against kind of spelling mistakes in your corpus. And again, it's the same TF-IDF vectorizer that we used before, and now you just give it a couple extra options, and you've got the same term frequency matrix for Engrams. So it's really easy. So now the next kind of stage, right? So we're comparing words between the two of them, but we know that there's similar words in English or in language that mean the same thing, but if the words aren't identically similar, the previous work wasn't going to highlight that to us. So we want to kind of start building in the idea of language. And latent semantic analysis is a really quick and easy way to do that. And basically all you're going to do is, if you're familiar with principal component analysis or singular value decomposition, but if you're not, it doesn't matter, you're just going to compress the matrix, right? So you've got this huge, big, long matrix of all the words in your dictionary with loads of zeros in there, and you're going to compress it down to a much smaller matrix. So for example, here I'm going to compress it down to just in 5 dimensions. So from 10,000 words, we're going to compress it down to 5 columns. And these 5 new dimensions are a compressed collection of words, which is another way of saying it's a topic, right? So all similar words are going to end up in the same column, right? And so you can, column 1 will be some collection of words that are similar. Column 2 will be another collection of words. So let's say this one could be about wood, this one could be about metal, this one could be about painting. And so the Home Depot website is going to compress down into a few topics. And again, this is really easy to do from the document term matrix that we had before. We're just going to use truncated SVD to compress that down to, in this case, 100 topics. And so that starts so we can do the same thing to the search terms. And now when we do the dot product again, we're saying that, let's say there was a search term, a product that has 50% metal and 50% nails. And there's a search term that has topics 50% metal and 50% nails, and they're going to overlap. So they might not have the exact same words. So if we just looked at word similarity between the two of them, we're going to get a terrible result. But maybe the topics are similar between them, so we can get a better idea of that there's similarity between the search term and the product, even though the words mightn't overlap exactly, if that makes sense. And so this is a really important part of this. Really jumps you up the next level of like building these topics in, of like getting the understanding of the human, like humans understand like these things are similar, because it's humans doing the judging at the end of the day. And so the next one is latent Dirichlet allocation. So it's very similar to LSA again. So you're doing compression again. You're doing compression of the term frequency matrix, but instead of just doing a principal component analysis where only a word can only end up in one bin, right? So that's a problem if you've got something like, I don't know, Office and Microsoft Office. Like they're two separate ideas. So maybe the Office should end up in both the topic for places in a building and Microsoft products. So latent Dirichlet allocation allows that splitting of words into different topics. So it's just a different way of looking at the topics. And then it also outputs, at the end here, it outputs the words that best represent the topic. So you can kind of look at an eyeball and say like, oh yeah, this topic makes sense, this topic doesn't make sense, maybe I should use more topics, maybe I should use less topics. So it's a nice way you can eyeball it and see, okay, the topics make sense. And then the coolest stuff, like this is the most entertaining part of it, but it's really interesting. So word to Veck is trying to do the same kind of thing, trying to compress down all of the words into a smaller representation. But instead of compressing the matrix, it's trying to spread the words out into a vector space. So it's trying to push the words out into some vector space of dimension, whatever you choose. So imagine 3 dimensions is trying to push all the words out into a 3-dimensional space, and so that all similar words end up in a similar place. And it does that by looking at the words surrounding a word. Okay, so if a word is surrounded by similar words, it'll get pushed out to that part of the space. So for example, brown is going to get pushed out to the space of the quick fox jumped, and fox is going to get pushed out to quick brown jumped over fox. So if you give it a huge corpus of text, it's going to start learning about not just topics, it's going to start understanding language and which words are represented close by. So yeah, like I said, I mean, similar words end up in similar places. So we can do a quick look at that, which you won't be able to see on the screen, but take my word for it. These are like measurements, so there's some inches up here and there's like a foot up here. This is to do with like painting doors. There's a big section of Home Depot, it seems. This is electricity related parts. So you can see that it's compressing, it's placing words into the right areas. But what's really interesting about Word2Vec that's different to the other ones is that you can start doing vector arithmetic, vector addition and subtraction with these vectors in the space. So woman minus man is the same as queen minus king, or verb tense, so walking is the same to walked as swimming is to swam. Country capitals will start coming out. I think there's some work on where you can take the words from English and they will map over to other languages. So whatever you've learned from English, that will map over. So it's really good for translation. So whatever you learn in different languages, you can start mapping it out to other languages. You don't have to keep training on just one or two different languages. You can start spreading it out over different parts. And what's really useful for us in this project is that there's some pre-trained models. So Google, there's one that's trained on the Google News network. And so that has an understanding of language that I can't get from just the Home Depot website. The Home Depot website, the topics are only the topics that are Home Depot website. I can use the Google News model and understand more about human language now, more than just the topics that are in there. So you can add that in, and it gives you it gets you closer to a human understanding of similarity between search term and product. So that was all of the features that we use in our model. So you're getting from word similarity to topics up to kind of a little closer to language, I guess. And so now we want to use all these features that we've built and start making a prediction. So we've seen our linear model did terribly, so now we want to use a more flexible model that will help us predict better. So most of the way through the project we use random forest because it's just easy. I don't know if anyone's familiar with it, but it's kind of like it's a decision tree. It's a collection of average decision trees at the base level. So it's really robust. It's really hard to overfit. It's really hard to get it to break, really. So it's really easy to use if you're focusing on the feature engineering. You can use the random forest for most of your work. And then near the end, there's a more flexible model called XGBoost, and I think there's a talk about that tomorrow, which would be really interesting because it's XGBoost. Melted my brain for a couple of months. It's really tough to work with. It gets the best results, hands down. It's really, really flexible, but it's really hard to work with. So yeah, I would recommend that talk tomorrow if you're interested in it. And our highest scoring submission came from not just looking at those features, but we just chucked a load of features at it, and it came out with a really good result. Sorry. The nice thing about these random forest and XGBoost models is that you can pull out the feature importances from it. So you can start to understand what's important about the data, what's important for making a good prediction. And so it's there can be you can overuse it maybe, I guess, because no, it doesn't matter. It's interesting to look at this one to see. Here's our original really bad linear model. Sorry, it's not linear, but here's our feature. You could remember the one we put up initially of just random dots all over the shop, and that is by far the most important feature in the whole model. So you can see like that. Maybe it looks terrible at the beginning when you're working with something. It looks like you're never going to get anything useful out of it, but actually it's a really important feature. And then you can see that there's one with Engrams, the term frequency matrix with Engrams, and the Word2Vec, and just the TF-IDF. That's just word similarity between the three of them. So you can see that all all at the top, all the most important features are title importances. And that implies to me that when the humans are doing the evaluation, they just look at the search term and they look at the title and they, yeah, it's similar enough, and don't dig into the actual kind of work. So that's the danger of when you're looking at human labels. And then you can see that there's a load of other features down here. The description, the product description isn't quite as important, but when the product description starts to become important, it's the topic type models. I know this is a tough one to interpret, but I thought the title beginning at the very top was interesting. Finally, how to win. Why didn't we win the model is because people have much better processes than us in it. So we had, I was one of those people when we started this, coming from academia and just ran the whole thing in a giant script. It's cringy to look back on it now a year later. But when the nice thing about Kaggle is the top 3 people are forced to write a blog post about it, so you can learn. Oh my God, that's really what we should have done. That's really interesting. That's really interesting. You can start learning from these guys and start taking the understandings that they did. And what they did was basically did loads and loads and loads and loads of models and essentially averaged them together and got wisdom of the crowds. So it's a really great learning experience. I think Kaggle. The community is really, really helpful. Loads of great ideas being discussed. Competition element helps you push further than you would normally. Like I said, I'm lazy, so I probably wouldn't have pushed, and you added in all those extra featers, so it gives you that extra incentive to get better. And then Python is really useful for this text analytics. I came from a competition before, did an OR, and Python was so much better. So yeah, that's, I should preach into the choir here, I suppose. Okay, that's it. I don't know if I've questions.
One question, can you go back 3 slides back? Yeah, this one.
Yeah.
So just one question, for the feature importance, is that the weight for the parameters?
I think it is the fraction of times it was used in all of the trees, but I'm rusty. Yeah. I think it's the fraction of it's out of 1, so it's all the features summed to 1, I think, and it's the fraction of times they were used in all of the different trees. But someone else better than me that should pipe up if I'm wrong.
Okay. Also another question, more general. So when you say you split the data into the training set and the validation set.
Yeah.
And I suppose they have both use errors, and how is there kind of a trade-off between the training set error and the validation error? And if it is, how do you see that? Like which one is the one that you're trying to minimize more?
So the validation error versus the one we put up onto the website.
Yeah, the training error.
That you really want to try and get one that's good on your own side, because they test on, let's say, 10% of the data, and at the very, very, very end, they test on the final 100%, and that's the final ranking. So you can find yourself dropping way down. So if you overfit to that leaderboard, you can end up dropping way down. So you want to get as good of a validation set on your own side and figure out when you're overfitting on your own side, rather than fitting to the leaderboard.
Thank you.
Yeah. Hi.
Oh, yeah.
About a question about the machine learning algos that you used. Did you use them as they are from the sklearn libraries, or did you have to re-implement some parts of them to fix memory performance issues?
No, it was all sklearn parts to it, and XGBoost is additional, and GenSim is what I use for the latent Dirichlet analysis and the word to Veck. So GenSim is a really nice package, not quite as intuitive as sklearn, but it's really great for text analytics.
Hey, great talk, thank you. So I'm actually curious, when somebody would implement something like this in practice, like a search engine. For a random query, I would expect in most cases to get a subset of the products rather than a single product, because they would all match the same.
Yeah, yes.
So when somebody comes, a human tries to do some labels for this data set, you would have multiple products that would match rather than a single one. So then, yeah, it's very hard to match what the humans do with a machine learning model, I would say.
Yeah. I think there's a lot of like human biases that are baked into it, and you're predicting the human biases, not the actual kind of relevance. I guess that was the difficulty of getting through this. Yeah.
So then, can we say that it's like a not so well formulated problem?
I think that's a lot of the time when you're on here. Yeah, just get Google to do it. I think that's that was the lesson.
Just wondering for the actual competition end, when they go to verify the performance of the model, do they use specific verification like scores, like skill scores? You don't know anything about
So they'll tell you at the very, very beginning, we're going to, this one was root mean squared error, or it'll be like log loss, or like depending on the question, it'll be some like standard error metric, and that's what everyone is aiming towards.
Oh, okay.
Yeah.
Cool.
And then at the end, you have to upload your code at the end, and then usually they won't use it because it's too over-engineered. But
Okay, great, thanks.
Hi. So, were there any limits to the memory consumption that it could take up?
no, you can use it as whatever you want. You can use a giant AWS server if you want. That's just going to cost you. I had a little 16 gig MacBook, and it did everything I needed to do. There's a really nice thing. I didn't talk about. There's kind of Jupyter notebooks on the website that people write their own scripts on. You can learn a ton from them, but there's memory limits on that. So usually they'll be kind of like around the middle of the leaderboard because they just have memory and time limits on them. But there, if you're like interested in learning about sklearn, NumPy, SciPy, or different things like that, go on to Kaggle website and look through the different scripts people are using. There's a ton to learn on there. Sorry, did that answer your question?
Yes.
The first part.
Hi, thanks for the nice talk. A quick question, like, did you do some analysis on the out of vocabulary words in your word2vec? Because in the final, like the ranking of features, it was on the top 3 and 4, but did you look like how many, when you were doing the overlap, like how many words were not there in the word2vec trained model, like out of vocabulary words?
I was using the full vocabulary in the Home Depot website.
No, but you kind of used the already trained Google
Oh,
Engram based model.
Yeah.
So there would be some mismatch words that you won't be finding for your word2vec from the Google Engram.
Yeah, I didn't actually check what I don't think I checked what the difference between the overlap was between the two of them. So yeah, there probably is like quite an overlap. There's not like going to be, I don't know, insulation bats in Google News.
Yeah.
But it still was useful enough to get a kind of just a different view on things. But yeah, I didn't do any analysis on it.
Yeah, because there are like some research and papers, like if you can like train your own embedding on your in-house data and you can add to the big embeddings which you have learned, so it kind of boosts the performance.
Yeah. I think that'd be the nice thing to do later on, is like have models that are retrainable, I think.
Thanks.
Hi, again, thanks for a great talk. You talked about latent semantic indexing.
Yeah.
Is that right?
Yeah.
Dimension reduction.
Yeah.
Are you able to explain in kind of plain English for slow people like me what that actually does to words? I can understand it in terms of dots on a graph.
Yeah.
But in terms of language and words, what's the intuition for doing that?
Well, you know that like in principal component analysis, it tries to collapse down dimensions that are similar or are correlated with each other. And it's the same with words. It's trying to collapse, like each dimension is a word, so it's trying to collapse down each dimension, which is a word, into correlated words, so that all of what's going to end up happening is each of the final dimensions you get out is going to be this giant linear combination of different words. So it's going to be, let's say one dimension might be like 0.5 metal, 0.5 metals, 50% nails, or something like that. You know what I mean? It's this like linear combination of words, correlated words. Words that are correlated words, I mean that they're in similar space, they're similar places.
So your new topics, which are the linear combinations of words,
Yeah.
you're hoping there's less of them to
There-
describe the data.
There will be less of them, and it describes the data because you're getting an understanding of topics. It's topic modeling.
I've been trying to start for 6 months. We just don't know.
I should get into teaching.